This is part 2 of chapter 2, where we look at using the t-distribution to do hypothesis tests for means, and also the normal distribution for doing hypothesis tests for proportion. Hopefully the first part kind of got you, up to speed about doing hypothesis tests in general. Anyway, so back to my lovely notes. Again, anytime you're doing a hypothesis test and you're dealing with a mean, but you don't want to estimate or guess what the normal distribution in the population is, then you switch to a t-distribution and you calculate the standard deviation from your sample data. So the example they give you on page 285 uses a file called invoices, which we'll look at when we do the pH stat part of this. But I can tell you that what we're assuming is that the average spent for the invoices is $120 per customer per trip to the store, and that in the sample that they take a sample of 12 invoices. They find that the actual average is $112.85 with a standard deviation, which they calculated of $20.80, and they choose an alpha level of 0.05. The research question then would be, has the average amount of sales changed from $120? So my hypotheses, my null hypothesis says no, it hasn't changed. It's equal to 120, and the null says yes, it's different from 120. So it's a two-tailed test. Using the critical value approach, your decision rule uses the t-distribution, and again, the t-distribution is going to be n minus 1 degree of freedom. You lose one every time you use something else from the sample, so we're using the standard deviation. So if you look in your in your t-distribution tables, and you look in the area 0.0250 in the tail, which is 0.0250, and you look under degrees of freedom, again with our sample size of 12, you look under 11 degrees of freedom, you should see the value 2.2010. That is our critical value, and since the t-distribution is symmetrical, just like the normal is, we have a negative 2.2010 on the left and a positive 2.2010 on the right. It's set up the same way it was in the other problem. We have two reject regions. One half of that 5% is in each of the tail end, and our do not rejects in the middle. Our formula for our test statistic is almost the same. The only difference is in the notation shown in the denominator. They use an S for standard deviation instead of a sigma that we used when we got it from the population. So your numbers all go in, and you end up with a test statistic of a negative 1.1908. And this value falls somewhere between the lower critical value and the upper critical value. So your decision from a statistical standpoint is do not reject your null hypothesis, because this test statistic is in between these two critical values. From a managerial standpoint, what you're saying is that the average amount spent per customer per trip to the store has not changed significantly from 120. There's a section in there you should read over on page 286 to 287 that says checking normality. We've talked about this before back in chapter 3, then in chapter 7, I think. So you should just go back and review that. If you're not sure it's normal, you should check it out. P-value, the p-value approach, we're not going to even try to do that by hand with the t-distribution, because we have to estimate using the t-distribution is not complete. So what we would do is we're going to go to pH stat, and my data, I already opened up the file invoices. It should be on your disk, so you can open that up. But you can see we have 12 invoices that we sampled, and we're going to go to pH stat, again, one sample test. This is a t-test, and our null hypothesis was that they were spending an average of 120. Our level of significance was 5%, and we are going to use our sample statistics unknown, and we're actually going to select the range of cells. It's only 12 Plus I did select invoice amount at the top. So this, make sure this is checked off. First cell contains a label. And this is a two-tailed test, so I say okay. And you should see, you know, the output you see here. So again, this is our test statistic, negative 1.1908. We already computed that. But the p-value, which we did not compute, Excel will compute for you, and it's 0.2588, which is definitely greater than your alpha level of 0.05. So our decision would be, excuse me, excuse me, do not reject your null hypothesis. And again, it's the same decision you got the other way. So anyway, that's how you do that. And you know, I put the output here. One-tailed tests work essentially the same way. The difference is that a one-tailed test, your whole level of area of significance, level of significance is in one tail end or the other, which of course changes how you get your critical value. And you just have to, again, you know, remember that what you're dealing with is one or two tails. So the example 9.5 on page 292, that's right, 292, they have an example where they're manufacturing chocolate bars, and the bar is not supposed to have a weight of any greater than 6.03 ounces. They're probably selling these chocolate bars as weighing 6 ounces, and they're just checking to make sure their production process is not over filling, you know, the chocolate bars. In other words, it doesn't weigh too much. So this is what we know, we think is there or should be there. So we take a sample of 50 chocolate bars, we weigh them, and they have an average weight of 6.034 ounces, and the standard deviation computed is 0.02 ounces, again at the alpha level of 0.05. So our research question is the average weight of the chocolate bars greater than 6.03 ounces, and you set your hypothesis test up so that it is a right tail test, and you're interested as to whether they weigh too much. So you put the greater than sign in the null hypothesis, and the less than or equal to sign, which should be there. Maybe that is there, I do not know, but let's go back and fix that. Insert symbol, less than or equal to 6.3 ounces. Maybe it was there anyway, I can't tell. Anyway, so, and you know, we're going to use the pH stat. So to use pH stat, you go back to Excel. I just need a clean sheet, and since I already was given this data, it wasn't a file, I go to, again, pH stat and one sample test, and this is the t-test unknown, and my null hypothesis is that it weighs 6.03 ounces, my level of significance 0.05. My sample size was 50 candy bars, and the average weight was 6.034 ounces, slightly above, and my standard deviation from the sample was 0.02 ounces. So the data was given in the problem. This is, remember, our hypothesis. It's a right tail test, upper tail test, so just make sure you select the right one. So if it goes greater than, it's an upper tail test, less than is a lower tail test. And I say, okay, and pH stat should do all these calculations for you once you have that. Anyway, so you will see that your p-value in this instance is 8%, which is, again, above your alpha level of 0.05. Anyway, that's how you do that. Then the z-test for the proportion. Anyway, that's my output, proportions. They work exactly the same way in setting up the hypothesis that the mean did. The only thing that changes is your population measure, which is pi, and you still got the three forms. You can have two instances. well, you can figure it two ways. I prefer this first way, and that's what we'll use is this. Uses the standard error of the mean in the denominator. We're familiar with that, and then that notation makes sense. So example 9.6 in the book, where we've got a population proportion that's 0.883, and then we take our sample and we 400, and we find that out of that 400, 378 observations said yes to whatever it is we're measuring here, which I think I've forgotten. But anyway, says yes, and drive-throughs. Oh, this is the number of orders that are filled correctly. So McDonald's reported they fulfilled 88.3% correctly. That's where that came from. So they took a sample of the next 400 orders, 378 were filled correctly. Alpha in this problem was given as 0.01, and the research question would be, they've changed the process. They want to know, has this new process increased the proportion of orders filled correctly? So your null hypothesis says less than or equal to 0.883, and your alternative said is greater than 0.883. Anyway, so in this case, we have 1% in the upper tail. So when we look this up in the normal distribution, we look up the area 0.9990, and you should see a critical value of 2.33 listed. So that's your cutoff, your upper critical value, and anything greater than that for a test statistic is in the reject HO range, which means it has increased, and anything smaller than that means it's not increased significantly or changed significantly. So to compute your P from your population, your proportion, you take the number of observed divided by your sample size. So what we've observed is that 94.5% are filled correctly. So you do your test statistic, and it comes up to 3.8579, and you can see that that's clearly over here in this reject region, which means we're going to reject our null hypothesis because our test statistic is greater than our critical value. Again, in managerial terms, you'd go back and you'd tell your boss that the change in the process has significantly increased the proportion of orders filled correctly. P-value by hand, you can do it by hand. I'm going to look at it using pH-stat. So if you want to do it by hand, go back and look at it, but I assume that you'd rather do pH-stat. So for pH-stat, let me add a sheet here in my little, all of our data was given in the problem. So we go to, again, one sample test, and this is a z-test for the proportion. My null hypothesis was 0.883. Level of significance in this problem was 0.01. And the number of items of interest, this is the number of, out of our sample of 400 that were filled correctly, that's 378. And our sample size was 400. This is a upper tail test. We want to know if it's actually increased the proportion. So we say, okay, and you should see something that looks just like, what you see here. So our test statistic, we already computed that by hand and compared it to our critical value, which is here. But again, what we're going to look at is the p-value, 0.0001, which is less than 0.05, which means we would reject the null hypothesis. Again, same result we got either way we did it. Anyway, that is, you need to read and study chapter 9, but that is what I think I need to tell you. Anyway.